This is homework 3, part B. So, in this video, we will be looking at a flat rectangular plate. Oops. And we'll imagine that this plate has some heat flowing through it and has a given length L. Okay. In order to understand the heat flow of this plate, we'll need to look at the Nusselt number, which is Nu. The Nusselt number tells us the ratio of convective heat flow to conductive heat flow. So and in our case here, we're looking at a flat plate with laminar flow. So we know the formula for our Nusselt number here is equal to 0.332, a value found experimentally, times our Reynolds number to the half power multiplied by our Prandtl number to the 1/3 power. Okay, so to put this into measurable variables, our Nusselt number, since it's convective, the ratio of convective heat flow to conductive heat flow, we know our convective heat flow will just be our convective heat coefficient, H, and the ratio will be to our conductive heat flow, or heat by conduction, K. And we'll just need to multiply by our length, given that we are looking at a plate here. So this will be the heat flow throughout our plate. The Reynolds number tells us the relationship between, the ratio between internal forces of a fluid throughout viscous forces. So what that looks like would be our density times our velocity times our length here, all divided by our viscosity. Our Prandtl number will tell us the ratio between our momentum diffusivity momentum diffusivity to our thermal diffusivity. So we discovered that our thermal diffusivity can be described as our thermal conductivity divided by our heat capacity times density. And then momentum diffusivity deals with viscosity. So we'll say our momentum diffusivity is equal to our viscosity divided by our density. So our densities will cancel here. And we'll be left with Prandtl number and physical properties of viscosity times heat capacity divided by thermal conductivity. So if we rewrite our Nusselt number equation in these units, we'll say our Nusselt number, so our conductive heat coefficient times our length divided by our thermal conductivity. So coefficient for heat flow by conduction divided by thermal conductivity times our length is equal to that experimentally found value 0.332 times we said our Reynolds number. So that'll be our density times our velocity times our length divided by mu. Raised to the 1/2 power. And that'll be multiplied by our Prandtl number. That'll be viscosity times our heat transfer divided by our thermal conductivity. And that is raised to 1/3 power. Okay, so in order to sort of understand how we can optimize our heat transfer here, we'll need to look at our equation just in terms of our coefficient of heat transfer by convection. So if we multiply this out, so we'll say H is equal to 0.322 times same thing and then this will be multiplied by what would be left of our Prandtl number. So thermal conductivity over our length. So okay, we can further simplify this equation. Say that our thermal or coefficient of convection is equal to 0.322 times our Reynolds number, which we can multiply out. So we'll say let me actually say density to our 1/2 times our velocity, length, and mu, viscosity, to the negative 1/2, multiplied by Prandtl's number, which will be our viscosity to the 1/3 times our heat capacity to the 1/3 times our thermal conductivity to the negative 1/3. And so I'll be multiplied by our thermal conductivity times our length to negative 1. So if we simplify these out, we can cancel our viscosity from Reynolds number, our thermal conductivity from Reynolds number, and our length from Reynolds number. And we'll be left with H oops. Density to the 1/2 times velocity to the 1/2. Then our length here will no longer appear. Our viscosity will be to the -1/6 because the remainder canceled out with the viscosity from Reynolds number. Say just our heat capacity left from Reynolds number raised to the 1/3, and then this will all be multiplied by our thermal conductivity times our length to the -1/2. Okay, so to optimize that heat flow, let me rewrite this question one last time. I'll just say density, velocity, heat U to the 1/6, and then length to 1/2. Okay, so in order to optimize that heat transfer, we can have the numbers in our numerator be as high as possible, which for some of these wouldn't make too much sense because our density is a state property. We don't have too much control over that. Velocity, we could speed up or slow down the fluid as needed. Same thing with our heat capacity, state property, so we don't have much control, and our thermal conductivity. Now, our viscosity is in the same boat, but the length, this is the length of our plate. So in order to have greater heat flow, we would maybe want to decrease the length of the plate. However, increasing the surface area would also increase the heat flow just because more heat will be flowing. So that is why it is better to have the long end of the plate perpendicular to the flow.